Now, a much trickier thing about n by n matrices is the question of inversion. So we say A is invertible, an n by n matrix, if and only if there exists a matrix B with the property that when you multiply on either side by B, you get to the identity matrix. So it requires the existence of a second matrix. Now, invertibility is a tricky business. In tricky business in matrix theory. Not every matrix is invertible. For example, the 0 matrix is never invertible, because if you multiply any matrix by 0, you get 0. If you have zeros in all entries, no matter what the entries of A are, when you compute the matrix product, you get 0. So there's no way I could find another matrix to multiply by 0 to get the identity, because any product with 0 is 0. So example 0, I is invertible. There's a good case. You take B is equal to I, and 0 is not invertible. But between those two, it's a tricky business. For example, for 1 by 1 matrices, it's an easy answer. But already for 2 by 2, it's quite complicated. So for 1 by 1 matrices, so the matrix just looks like A is invertible if and only if A is not equal to 0. And then the inverse matrix is just given by the entry 1 over A. That's the only thing you could multiply A by and get to the identity matrix, which is just the thing 1. So a real number is invertible if and only if it's non-zero. For 2 by 2 matrices, turns out to be as invertible, I'll just give you the answer, if and only if a certain quantity is non-zero. Namely, if you take the product of A by D and you subtract off the quantity BC, it's not equal to 0. And in fact, if that's the case, I'll write down the inverse matrix for you. Usually, if you don't want to just know if a matrix is invertible or not, you want to know what its inverse is. So if this is A, then A inverse is equal to 1 over AD minus BC. And you can write that real number down because this number was non-zero, so it has an inverse, times the matrix D minus B minus C A. And this means you take the scalar product of this matrix by that real number. So we can check that. We ought to do at least one matrix multiplication in class to see that I can do it. So let's multiply the matrix A, B, C, D by the matrix D minus B minus C and A. Okay, the entry here. I go across this row and down this column. I get AD minus BC. The entry here, minus AB plus AB. So the entry here is 0. The entry here, I go across this row and down this column. CD minus CD, 0. And the entry here, I go across this row, and here I get minus BC plus AD. Same thing, AD minus BC. So if I just took this matrix, I can multiply by my matrix and get something which isn't the identity, but looks pretty close to the identity. Namely, it's a scalar multiple of the identity. And the only problem might be that this scalar might be 0. But if this scalar is non-zero, then I could have taken this matrix and multiplied by 1 over it, and I would get the identity. Okay? Now, in general, the answer to the question of whether a matrix is invertible or not is the following. There's a certain function from the set of n by n matrices to the real numbers called the determinant, which I'll write just det, which maps n by n matrices over the reals to the real numbers. And the determinant of a matrix is a polynomial in its entries. It's a polynomial of degree n in its entries. So for example, this is the determinant of the 2 by 2 matrix A. And you probably know the formula for the determinant of a 3 by 3 matrix, or even generally the formula for the determinant of an n by n matrix. It's given by a formula. Determinant of A is sum over n factorial terms with a plus or minus 1 in front of it, and then products of n matrix entries. So n factorial here is just 2 terms, but if you go to a 3 by 3 matrix, there are 6 terms in the determinant expression. 4 by 4, there are 24 terms. In short, it's a useless formula, because once you get to 10 by 10 matrices, you don't want to be dealing with 10 factorial terms. Nonetheless, there is such a formula, and the key fact is A is invertible if and only if the determinant of A as a real number is not equal to 0, in which case there's a formula for the inverse of A. And the formula looks very much like this formula. The formula then looks like, you get, in fact, there's always a matrix. There is a unique matrix. That means there exists a unique matrix B such that AB is equal to BA is equal to the determinant of A times the identity matrix. There's always such a matrix. You can't always multiply something to get to the identity, but you can always find a unique matrix where the product is the determinant of A times the identity matrix. Well, no, I shouldn't say unique. I mean, if A were the 0 matrix, then anything would work. So, sorry, there exists there's a natural matrix. Let me just say that. And that B is sometimes called the matrix of cofactors. And you get its entries by taking partial determinants around A. Have you all seen that once or twice? So this is the matrix, for example, of cofactors of the original 2 by 2 matrix A. So there's always a matrix you can find where you multiply to get the determinant. And if this is non-zero, you divide B by the determinant, and you found a matrix to multiply through to get the identity. So please review this kind of determinant and inverse topics. We don't need the exact formula for the determinant at this moment, although when we start doing linear algebra in a more sophisticated way, I'll tell you what the determinant really is. This formula is about as useful as the formula for products of matrices where you sum over K, etc. What you really want to think of them as composition of transformations. This determinant is really the action of a linear operator, not on the original vector space, but on some vector space which is one-dimensional that's constructed from the original vector space. And when you have an action of a linear operator on a one-dimensional vector space, it gives you a scalar. That's the determinant. We'll get there.